Thank you everyone for joining us today for the OpenMP webinar, Mastering OpenMP Performance. This presentation will be 1 hour long. Should you have any questions during the presentation, please put them in the Q&A feature located on your Zoom toolbar. You will be able to see questions from other attendees, so please feel free to upvote or like the questions that interest you. This will help us determine which questions to address live at the end of the session. Any questions that weren't answered will be addressed post-event. Please watch for an email tomorrow with further information and a link to the recorded presentation. And now I'd like to turn it over to Ruud van der Pas. Ruud?
Hi, Lucy. Thank you. Well, welcome to this webinar. I have an awful amount of slides to show, to push through in the hour, so let's get started. All right. A little bit about myself. My background is in mathematics and physics. I worked at several companies. I started my career at the University of Utrecht. And currently I'm at Oracle. I work in the Oracle Linux Engineering Organization. But this talk is all about OpenMP, and I've been involved with OpenMP since day one. I was at SDI at the time, and I thought that's really interesting. And I got hooked, and I didn't leave since then. So I'm very passionate about anything related to application performance, especially, of course, the technical HPC type of applications, and OpenMP in particular. And today I hope to share some of my performance experiences with you. Before I do that, just a little bit of general information. I'm sure you all know this website, and if you don't, please bookmark this, www.openmp.org. That's your place to go. That's your one-stop place to go for anything related to OpenMP. For example, the specs, the 5.1 specs that were released in November, you can find them online. If you really like paperwork, you can also order your copy at Amazon. It's sold, I think, at cost, but be aware it's a 1.7 kilo heavy document, so you don't want to carry that on your travel, I think. All right. Just in case you want to have some food to read, this is an older book that I was involved with. I still think it's quite useful if you're new to parallel computing. It doesn't only cover OpenMP, it talks about other things related to parallel computing, but it doesn't go very far as far as OpenMP goes. If you really want to get into the OpenMP basics, I can highly recommend this book. The OpenMP Common Core. That's really a really good way to get started with OpenMP. Once you have some more experience and you have some more questions about features, you may want to look at this book, The Next Step. It covers 4.5. So one question I often get, well, how about 5.0, 5.1? Well, my answer is very simple. If you don't understand 4.5, don't even think about going further. So this book will get you up to speed on pretty much sort of the modern OpenMP. In this first part, I want to talk about a sort of random collection of tips and tricks, things that I picked up along the way. I try to make it very practical. It's pretty much all based on real life experiences, but I do try to kind of strip it down to the bare essentials and zoom in on the pain point. So the examples that I show are often quite simple, but keep in mind that they're derived from usually a much more complex environment. In the second part, I'm going to touch upon that somewhat more about the complexity of the tuning. First, I want to go through what I call my frustration slide. There's a persistent myth that OpenMP does not scale. At conferences, people still claim that. I see horrendous claims made. And it's very persistent. So I keep on talking about that. Because when you think about it, OpenMP is a programming model. Programming model is like your cookbook. You have your ingredients, and with that, you're going to make your recipes. So if you blame the ingredients for failing your dish, I think something is wrong. But that's exactly what you do when people say OpenMP doesn't scale. Of course, there could be things that may impact scalability. Of course, there can be very poor performance. For example, it could be that the compiler you're using, a library, or some other software has a glitch, and unfortunately you get hurt by that, and you'll see less than optimal performance, or even worse. That can happen. Or there could be what I call a mismatch between the system and the resource requirements. And a simple example is if your application requires a lot of bandwidth and you start adding threads, how many threads can the hardware actually sustain? So if that's not sufficient, if the bandwidth is not sufficient, you can start adding threads at some point and you won't get any benefit, or maybe even the performance degrades because of contention. So these things can all happen, but it's not related to OpenMP. The biggest reason why OpenMP applications don't scale is often that I find it's the user. You did something wrong, and you didn't know it was wrong. Nobody told you, and you're not aware. There are a lot of things happening under the hood, hidden to you. So this is not about blaming people, but it's about seeing that people write sort of bad OpenMP. And what I hope to do in this talk, this is a fairly basic introductory talk, is give you some guidelines how to avoid the most common pitfalls. So we're going to talk about how to get good performance, the basics. And my claim is, if you follow these guidelines, you should expect decent performance. And what do I mean with that? You get good performance out of the box. So an OpenMP compiler and the runtime system should do the right thing for you. It should do what you expect it to do. You probably won't get blazing scalability to thousands of cores, but as if you would ever have to go to the OpenMP performance court, the lawyers there will have no case against you. You did everything according to the book. So again, what I'm going to talk about will definitely get you going and improve the scalability of your application. Now, it all starts with the ease of use of OpenMP. That's a mixed blessing. I really like it. I think it's a great choice, but with the choice comes the downsides. On the pro side, what I like is that any idea I have is very easy and quick to implement. I get an idea and trying it out with OpenMP is usually not that hard. That's really, really good. It gets you to your solution much quicker. But you need to know that some constructs are more expensive than others. And again, if nobody told you, how can you know? So that's a big part of this talk, of course. Another thing is, if you write dumb code, you probably get dumb performance. Actually, I'm going to make that stronger. You will get dumb performance. And why do I say that? And when I say dumb code, that's at the OpenMP level. If you write inefficient OpenMP, there's often very little the compiler can do to fix it. We all sort of start being spoiled by very smart compilers that fix up things that are not optimal for performance. They just make it go better for us. At the OpenMP level, that's much, much harder. That's almost a talk in itself. But be aware, you tell OpenMP to do something and it will do that. You say, run this loop in parallel. It will run that loop in parallel. It won't question you, luckily. But that means that the burden is on you to make sure that makes sense to do and do that in the right way. So that's another thing that I quite often see. People don't write efficient OpenMP, and there you go. The one thing is, don't blame OpenMP. Goes back to the previous slide. OpenMP just gives you the ingredients, and it's up to you to make your own dish out of it. And whether that's tasty dish or not, that's on you. So let's get specific. Some guidelines how to not write dumb code. Well, it all starts with single thread performance, and that's one of those things that few people talk about. But when you start parallelizing your code, there's some homework you need to do. And part of that is that you have to pay attention to single thread performance. Why? Well, if your code performs badly on a single core, what do you think will happen to 10 or 20 or even more? You think it'll go better some magical way? No, it won't. In my experience, if the performance is poor on a single core, scalability gets to be much, much harder. So spend some time on improving single thread performance. How much time you want to spend on that and what you're going to do, that's completely up to you. But remember, if the program performs poorly on a single core, parallelization may be harder to get efficient. And that's the thing that can be very sneaky, that your code may actually scale well, because of course, poor performance masks scalability issues. If your code is so slow, nothing else matters. So some extra OpenMP overhead won't matter. So what we see in practice is that the slow code tends to scale well, but at the end of the day, it's still often slower than a more efficient algorithm, for example. All right. Rule number one sounds so simple, so obvious. Don't parallelize what does not matter, but it wouldn't be the first time that I see somebody who sort of parallelized everything in their code. And guess what? They also parallelized what was not relevant and actually may be inefficient when executing in parallel. So that's not a good strategy. It not only saves you time, it can actually hurt performance. So always use a profiling tool. Pick whatever tool you like, I don't care, but use a profiling tool to guide you where the time is spent. And what you do, you're going to parallelize where most of the time is spent. Again, sounds very obvious. In too many cases, I don't see that happening. Another golden rule is don't share data unless you have to. Sharing data in OpenMP is really wonderful. I really like it, but it can hurt. And I'll talk about that later on in this talk. There are some cases where sharing data can actually cost you performance. So the recommendation is use private data as much as possible and only share when you have to. And when you do that, you already have come a long way on getting good OpenMP performance. Another thing, and I'll zoom in on that in a minute, what I call think big. Maximize the size of the parallel region. A parallel region is inherently expensive. So a lot of things happening that you don't see, but that need to be done. So there's a cost associated with executing a parallel region. The more parallel regions you have, the more of that cost, which is purely overhead, will go onto your bill. So try to put as much work as possible inside a parallel region. And when you do that, you may make good use of constructs like single or master, where one thread will do the work only while the other threads are waiting. So you can put sequential work inside a parallel region using those kind of constructs. Another thing is minimize the number of times a parallel region is encountered. Don't bury a parallel region deep inside the algorithm in like a deeply nested loop, so that each time you hit that parallel region, you hit the overhead over and over again. Try to push the parallel region outward and have it executed as little as possible. To get a little more specific on that, one parallel for or parallel do is fine. Multiple back-to-back is pure evil. And let me show you an example. This is what I see in too many applications. And again, it's not about blaming people. If nobody ever told you, how could you know? But let's zoom in on this. We see a bunch of for loops or do loops in Fortran, and each loop has been parallelized with a parallel for. Now, there's a little thing with the parallel for. The parallel for is a fully fledged parallel region. So what we have n parallel regions here with all the costs associated. So that's bad. But what's maybe even worse is I can't use the no wait clause. As you probably know, the no wait clause leaves out the implied barrier at the end of a construct. It's a really, really nice feature. I like it a lot. I use it a lot. But the parallel region, for good reasons, has an implied barrier at the end, and you can't get rid of it. There's no wait for the parallel region. Again, that makes sense, but it is expensive. So this is not the right way to do this kind of coding. What I would recommend is create one parallel region. That's the Pragma OMP parallel at the top line. And inside, use the Pragma OMP 4. And with that, you can just parallelize the individual loops. And in a few places, there may be a room to use the no wait clause. In particular, the last one, the end of the parallel region has an implied barrier. We know that. You can't get rid of it. So that means that if I wouldn't put a no wait on the last loop, I would have a back-to-back barrier. Now, admittedly, that second barrier is going to be fast, but it will still take you time. And then think about scalability. As you go to higher thread counts, those costs start to add up. So that's not a good idea. One little warning, I've seen people do this and then they've got surprised because what they would do the Pragma OMP parallel for inside the parallel region. That's called nested parallelism, and that's not a good idea, certainly not in this context. So use the Pragma OMP 4, not the parallel 4, and you'll see this will be much more efficient. You have much less overhead. You only have one parallel region, and again, you can fine-tune the code using the no wait clause. So one of the basic things is once your code is running and you get the right results, start looking for where you might use the no wait clause. It's very powerful, but of course, the challenge is on you to do that in the right way. If you make a mistake and the no wait clause is not allowed to be used, you'll probably get a data erase. So be careful, but again, keep in mind it's a very powerful feature. Another thing that people often overlook is the schedule clause. If not all threads do the same amount of work, we call that load balancing issues, and then the schedule clause can be very nice to help out with that. With all of this, again, and I'll say that over and over again, use a profiling tool to guide you. Where should you look for an opportunity for the no wait? Well, the profiling tool will tell you. That's where you spend most of your time. That's where you start looking for an opportunity to use the no wait. I want to show an example. I wanted to do that as early on as possible. And this is taken from a graph analysis benchmark code. And what I'm showing here is a timeline. That's one of the tools that I use. And what it shows is a color-coded representation of the execution of your program. That very green top bar is the operating system view on the application. And essentially green means good news. So the operating system level, this application is running fine. Time is from left to right. And what we see is, what we show here is the call stack of the program at certain intervals. And that's kind of like that hairy part in the beginning. That's the initialization phase of the code and where the graph is being generated. Then we see all those wild spikes. That's a recursive sorting function being called there. So by looking at this kind of chart, you can get a feel for the dynamic behavior of the program. And what we see here is the first part is the graph generation. And then this program, it's a benchmark. It will do a BFS search and verify the result for 64 random keys. And I used the color highlighting to gray out everything I don't care about. So that's why you only see a few colors here for the call stacks. And what we see is the alternating red and blue, which means it is a search, a verification that the result is valid, another search, another verification, and so forth, 64 times. That's the key part of this application. So that's what we call the timeline view. It gives you a very good overview of what happens dynamically as you execute your program. Now, this is an OpenMP program. So I ran it on 4 threads, and I have the same kind of view. You see the initialization phase, you see that sorting, that recursive sort, but I'm going to ignore that. I'm going to look at the search and verification. And what we see now, as we execute on 4 threads, we see gaps in execution. At some point, there's nothing happening other than the main thread. The main thread is always executing. The other threads have gaps in execution. That's sort of magnified when you zoom in. You actually see those gaps. There's literally the 3 extra threads. They're not doing anything. That's really bad news. And when you look a little deeper, you see that's always while the red function is executing. So each time the red function is executing, for some reason, other than the main thread, there's nothing happening. That's really bad news, and it's all over the place. So that's the first immediate observation you make from looking at this kind of view. I can sort of prove this by looking at the CPU time distribution. I'm plotting here how much CPU time each thread takes. So when I have 2 threads, the main threads take nearly 800 seconds, and the second thread only close to 600. So that's a big difference between how much CPU time each thread takes. And as you increase the number of threads, it sort of gets worse. So when I look at the ratio of the maximum and the minimum CPU times, you see that ratio increases as the number of threads grows. In other words, the load imbalance gets worse as we add threads. So that's not a good situation. Okay. Zooming in, the tool told me this is where you spend a lot of your time. And this is pretty ugly code. I wanted to show it because that's real life. Not everything consists of the stream benchmark after all. So this is even a stripped down version of the real code. And there's a couple of things to observe here. First of all, we see the OMP4. So that's a fairly bulky OpenMP4 loop. And the outer loop is a fixed length loop. It runs from K1 to old K2 minus 1. So that's okay. The second loop is irregular in length. The length depends on some data structures that depend on K. So potentially the length of the second loop is not a constant. Another thing we see an if statement, And in case that if statement is true, there's a fair amount of work being done. There's even a compare and swap. There's potentially some copying of data going on. So if that if statement is true, there's a fair amount of work that could be performed. And that's what we call the irregular control flow. Well, in other words, what that means that if a thread picks up an iteration for k, the amount of work it does could strongly vary compared to another value of k. So this is a classical example of a load imbalance, and that's what we saw when we had those gaps. Now, the thing is that loop was parallelized with a simple OMP4, and the specifications say that then you get some default scheduling, and for efficiency reasons, that quite often is static scheduling. Static scheduling is very efficient to implement, it's very efficient at runtime, but it's very rigid. So you get load balancing issues like in this case. A better choice would be to have a more dynamic loop schedule clause, like dynamic or guided. Or if you go that way, my choice is to use the runtime clause so that I can set the actual schedule at runtime through an environment variable. So that way I don't have to recompile my code all the time. And that's exactly what I did here. And I ended up with setting the dynamic schedule and a chunk size of 25. So each time you get 25 iterations. How do you know the chunk size should be 25? Well, I could be very fancy about it, but essentially it's crystal ball, trial and error. You just got to try, you pick a few values, you use some bisection technique to find out where, what helps. And of course, the 25 is not carved in stone. I'm quite sure if you use a 24, or 26, or something around 25, you'll get similar performance. It's usually not that sensitive to the value, but you know if you would pick 50, it probably wouldn't be good. So yes, you have to do some experimentation in cases like this, and that's why I like the runtime clause, because I can just do that through the environment variable, not having to modify my code all the time. Think about that. It's a very nice feature to use. It definitely pays off. What I'm showing here is the search time. That was important for this benchmark. So the BFS search time in seconds, that's the bar chart. And the dotted lines, that's the parallel speed up, normalized to the single thread performance. So what we see here is that the original code in single thread is actually a little bit faster than the new code. Why? Well, there's a cost for the dynamic schedule. The dynamic schedule is more expensive at runtime. And what we see a tiny bit of a slowdown. So small that I really don't care, but I wanted to point it out that yes, the single thread performance takes a little bit of a hit. But then as you start adding threads, you can definitely see how much the search time improves. Compared to the black dotted line for the original code that barely showed any improvement, we now get near linear scaling for up to 8 threads. I was running this on 8 cores only, with hyperthreading enabled. So beyond 8 threads, I see that I still get a benefit from hyperthreading, which is kind of nice. You can't always count on that. But of course, I've reached my maximum gain when I went to 8 in a way. So I got a little bit extra boost, and ultimately, my code is 3 times faster than it was before. So now think about that. What did it take? A profiling tool to tell me what's wrong. And the only change that I made here was to change the loop scheduling strategy from static to dynamic and a chunk size of 25. So a very small change and quite a big improvement. So, all right, what's really important? Always do what I call the sanity check. Always verify the behavior. We see that this is working out well. Did we indeed tackle the problem? I can just highly recommend to verify that. And that's what I'm doing here. I'm comparing 2 profiles. The top one is on 8 threads using the original code. You see all those gaps. And on the new version, that's the lower bar, you see that those gaps are pretty much gone, at least in the visible view range. You may see them when you zoom in. So this is not telling the whole story. So what I did, I again looked at the CPU time distribution across the threads. While we had that big gap in the original case with dynamic scheduling, the CPU time is pretty much distributed equally. So the gap is indeed gone. It's not only optical illusion, it's actually really gone. All right, let's continue with the recipe. I can't stress that enough. A barrier is useful and you need them, but they are expensive. So use them with care. So think about no weight, or if you use an explicit barrier yourself, be careful when to use them. The same is true for locking in critical regions. You absolutely need those in certain cases, no doubt about it, but be careful and specifically look at atomic operations. Unfortunately, I find that not many people know that OpenMP has atomic operations, atomic constructs, I should say. Those atomic constructs leverage atomic instructions inside the machine. They're much more efficient. So instead of using a critical region, sometimes you can use an atomic operation and it's way more efficient. So think about those things. In the end, Amdahl's law is still valid as ever, so everything matters. And I'll get back to that later, but don't leave anything on the table. If you see something inefficient, even if it doesn't help you today, it may help you tomorrow as you go to a larger system. So pick up everything you see and fix it as much as you can. Another golden rule is don't use nested parallelism. I know some algorithms benefit from it from a functional point of view, but if nested parallelism works for you, start looking into tasking. Tasking is a much more flexible, much more fine-grained system than nested parallelism. Nested parallelism was in OpenMP 1.0. It wasn't bad, but by now you have better alternatives. Especially remember when you start nesting parallel regions, you also nest the barriers, and that can get very expensive very quickly. Again, like I just said, look at tasking, much more flexible. For example, the loop I just showed, one of the things I want to do is see what happens with the task loop. Task loop is a nice feature to leverage tasking on a loop, and it may do better than dynamic. So I'm going to look into that. So maybe in a future webinar, I can report on that. And I want to zoom in on what I call the harder part. What I just gave was some sort of checklist of things to do and not to do. I'm now going to talk about memory access. As you all know, in OpenMP, memory access just happens. You need some variable A, you'll get it. Okay. There are two things to watch out for, though. And one of them is performance loss caused by a non-uniform memory access architecture, or Numa for short, or false sharing, or both. Well, hopefully that's not the case, but it could be. So there are two things that may impact your performance. They're at the memory level, and they just happen. They're sort of sneaky because you don't really see it. It's not like a barrier that you stick in and sort of sticks out. It just happens. And I'm going to spend quite some time on that, on those memory things. I want to stress that both of them have nothing to do with OpenMP. They're a result of using a shared memory architecture. So you could write the examples that I'm going to show. You could equally write them in, let's say, P threads or Java threads, and you'll see the same bad thing happening. It's just that you happen to use OpenMP, and that's then it shows. But again, this has nothing to do with OpenMP. It's because we're using a shared memory architecture. Okay, so both may have a pretty big impact on performance. Now, the second part of this talk, which is imminent in a few minutes, I'm going to talk about Numa almost exclusively, so I'll skip that for now. I want to finish this part one with what we call false sharing. It's a bit of a funny name when you think about it, but it's definitely something you don't want to have in your application. So what is it? We talk about false sharing when multiple threads modify the same cache line at the same time. In other words, they're hitting on a small portion of relatively small portion of memory, all of them at the same time, and they're modifying it. And that can happen in some sort of unexpected ways. You may never have thought about it, but I'll show you a very simple example how easily that can happen. But what happens with false sharing is that the cache line will move through the system because the thread can only make a change when it has the cache line of where the data is in its cache. So if that cache line happens to be elsewhere, it'll have to go and fetch it. Now the hardware will take care of that, luckily, but it still takes time. And you can imagine if this happens on a large scale, on a large machine, this will impact performance, and it does impact performance. Okay. There's also an extra cost that you have to update the state of the cache line, that the cache coherence updates. But the biggest thing is that cache line starts traveling throughout your system. Now, false sharing happens a lot. And if it happens once in a while, that's fine. You won't even notice it. The problem is if it's in the heart of your algorithm, then it's not okay. And you will see very poor scalability. False sharing tends to hurt performance very badly. So here's an absolutely trivial example that shows false sharing into action. I have a parallel region and I have a shared vector A. And what I'm going to do, I'm going to initialize A to 0, and each thread will initialize its element to 0. So I get the thread idea, and that element is being assigned to 0. Very, very trivial. The problem is that update of A has all the ingredients, all the components for false sharing to happen. We do that presumably at about the same time. This is a tiny array. Even if you use 1,000 threads, it won't be more than 8 kilobytes. So you have a tiny block of memory hit upon by all the threads at the same time. All the conditions for false sharing are met here, so that update suffers from false sharing. So here's what happens in runtime. At runtime. So let's say I have 4 threads. So A has 4 elements, and time is from top to bottom. Presumably, let's say thread 0 does the first update. You don't know, but that means it will find the cache line wherever A of 0 is, find the cache line, get it into its cache, and do the update. But then, at the same time, thread number 3 will want to do the same. And then the hardware will arbitrate between that. But at some point, this other thread will need that cache line, that same cache line that vector A is in. So it'll have to get the fresh copy of that line, move it to its cache, and do the update. And then history repeats. So each time a thread will do an update, it may mean that it will have to get a copy of that cache line from somewhere else in the system. And if that's a large system, that could take a while. Even if it's a small system, this is actually already expensive. So that's called false sharing. I won't say anything more about it. It's the last thing to check. If nothing else explains your poor performance, think about false sharing. I wouldn't think about it right away, but I've had several people that after I'd mentioned this, they would tell me, oh, now I know why my code is not performing well. They were suffering from false sharing. All right, brings us to a first tuning strategy. I try to give you practical advice in this first part, and I would just take a look at it and follow them and see if you can do something about it. Give it a try. Don't forget, make a profile before and after. Always make sure that indeed you tag that made things. It's always a good practice. Make a profile before you begin, but always after as well. Sometimes the details. So this is not sort of carved in stone. Some nasty detail can make all the difference. If you have this performance mystery, so you don't know what explains it, think about Numa, false sharing, or in the worst case, or both. That's not very likely, I hope, but you can't exclude it either. All right. As I said, I'm on a tight schedule. I want to move on to the second part where I try to get closer to the real world. Okay. I want to again show several tuning examples. They all sort of bear some relevance to real life. And the first challenge is when you start tuning in code, and anybody who has done that knows that, is finding out what goes wrong. What I show you here is the final result of an analysis. That can be a lot of work. So I show you some isolated cases, but in real life, the situation could be much more masked and hidden. Okay. The last part is a completely worked through Numa example. So more examples. Here's one. And all of this is picked up from real code, so I didn't invent this. The single region, I have some code in there, and then the end, and followed by a barrier. Okay, looks fairly innocent code, but it's wrong from a performance point of view, because that second barrier is redundant. The single has an implied barrier. So what we have two back-to-back barriers, and admittedly, the second barrier is going to be faster, but it's still taking you time. And as you add threads, the cost of that will go up. So why waste it? Just remove it. It was not necessary in this code. And again, a compiler will not do this for you. If I'm wrong, please correct me. Send me a mail. But so far, what I've seen is compilers will just do this, and this is not because the compilers are not smart. It's just because the way things happen. As I said, it's a whole talk in itself. Maybe one of the webinars should be about those things, about the compiler view on OpenMP. But in practice, it won't even do this very simple optimization. You certainly can't count on it. So don't write it. And if you have it, remove that second variable. A much more complicated example where you potentially do more work and still save time. Now, when you start doing more work, you always got to be careful because the balance can quite quickly go into the wrong direction. Not in this case, and that's why I want to show it to you. This is from a real code. What it does, it starts initializing one array, one vector element at index endpoint. That'll go into a parallel region, fairly large parallel region. I only show you the relevant part for this, this case study. There's a for loop, and that for loop runs from 0 to endpoint -1, and it initializes a to -1 over that range. Then there's a second for loop, and it starts at endpoint +1, so it's not doing the update on endpoint, of course, and it's initializing to -1, and then there's a whole bunch of code following it. So this was sort of the OpenMP structure. Now, what's wrong with this? First of all, both OMP4 have a barrier. Looking at it, you can use a no wait on the first one. I'm not sure about the second one because it depends on what happens next. But those two updates are independent, so there's a no wait missing. We got at least 2 barriers in these OMP4s. You have the overhead for the OMP4, which is not that big, but again, everything matters, so why waste it? The big thing here is that the performance benefit depends on n, the overall loop length, and the value of endpoint. If endpoint is small, the first loop is short, and that means it's probably not a good idea to execute that in parallel, certainly on a whole bunch of threads. If you're using 100 threads and endpoint is 20, that's not a very good idea. Likewise, if endpoint is large, then the second loop is short. So, as this code was sort of sliding through the value of endpoint, there's going to be a lot of cases where either one of these loops is inefficient. So that's not a good idea. Okay, let's go back to the drawing board. That's often what I like to do, sketch things like what's really happening here. What are you really trying to accomplish? Well, it starts with this. At index endpoint, a value is assigned to A. Then you have that block of A, 0 to endpoint -1, initialized to -1, a barrier, another block update, and another barrier. That's what the current code is doing. But when you look at the final result, this is the final result. And then I realized, wait a minute, I can do better than that. So what I can do, and that's the idea, I just blast -1 into that whole block of memory, and I do a single correction at the index endpoint. So that's the idea you get. And as I said in the beginning of this, this talk, that's why I like OpenMP. Implementing that idea is really easy. The new code looks like this. I now have a single for loop running from 0 to n-1, blasting -1 into that vector. And in a single, I do the update. So I correct that one element. And that's why theoretically you're doing more work. You're doing one extra assignment, which is absolutely nothing in terms of extra cost, but the saving is substantial. So of course I have I could use the no wait, and I can't use the no wait on the first loop, by the way, then I will get a race condition. So I could still, in this case, could still shave off one barrier. I only have one for loop, so I have a reduced overhead. But the big thing here, of course, is that now the performance only depends on the value of n, which presumably is related to the problem size that I'm solving. It's like this case, the size of the graph. This is from graph analysis as well. So presumably that's large enough to make parallel computing worth doing. So I eliminated the dependence of the performance on this thing called endpoint. All right, so these were all still fairly basic things. I think if you stare long enough at the code, you'll find them. And The one complicating thing is, as I said a few minutes ago, is that it may be hidden, the code will be ugly, so it may take some time to really find out what's going on. My recommendation is be patient. Keep on staring at the code, keep on trying things, and tackle issues one by one. It's probably an iterative process. You make a change, and sometimes you see a gain. Sometimes things go slower. I could give endless talks on how I've made codes run slower, but you're probably not very interested in that. But such is real life of tuning. You get a brilliant idea, you type it in, and it's worse. And later you realize it wasn't that brilliant after all. So that's all part of the game, but it does go into the tuning process. It's just part of it. It's not all kind of clear cut. The last part of this talk, I want to talk about Numa, and especially since about almost every system shipped these days has a Numa architecture. It used to be only the very large servers had a Numa architecture, but nowadays your two socket box, or even your single socket box can have Numa inside the socket. So it's everywhere. So what's Numa? Numa means that memory is physically distributed but logically shared. So the memory chips are scattered over the system, but to you it appears as one single memory. Okay. Sharing data is transparent. You don't know where the data is, you'll just get it somewhere from wherever it is in the system. It doesn't matter, unless you care about performance, of course. If you care about performance, you gotta have some notion of where your data is and try to avoid it moves away too far. So that's going to be the bulk of this example. I start with showing a fairly generic Numa system. I'm showing you a system here that has 4 nodes. Each node is like a parallel computer in itself. It has a bunch of cores, those are the green boxes. It has a lot of several caches, but there's always like a last level cache, and typically in this kind of architecture that's shared. So all the cores have access to that shared cache. It's called LLC, last level cache, and that connects to a portion of the memory. What we see here is the memory is split in, each node has 25% of the memory, and there's some glue in between, the cache coherent interconnect. That glue makes it appear to us as a single memory. So to you, when you use top, it will just report you the total size of the memory. But in reality, in the physical world, it's split it. And the cache coherent interconnect makes it all work. You need something, you'll get it. All right. So to the developer, this is what the system looked like. You have places where you can run your threads, where you can store your data, and through some magic, it's all connected. But from a performance point of view, we got to start, we've got to be careful, because there's a notion of local versus remote access times. So let's look at a simple example. Let's say my node is executing somewhere in that system, and that's the purple box, that my thread is somewhere executing on a core somewhere in that system. Well, where could the data be that it needs? If the data is all in the memory connected, directly connected to those cores, I get the fastest memory access. That's what we call local access, and that's the best you can do. You can't do any better, that's the goal. That's what you want. But how do I know? Maybe my data is somewhere far away in a corner of the system. Again, the hardware will take care of it. You will get that data to you, but it could take a long time on the scale of things. So that's Numa in a nutshell. And what you really want to do when using a Numa system is avoid that second situation. You want to avoid that your data is far away from where you're executing. So it's all about keeping the data and the threads close. And in OpenMP, the choice was made to move a thread to the data instead of the data to the thread. And the reason is very simple. It's a lot easier and cheaper to move a thread than move data. So the model in OpenMP is that you have the data somewhere, and what you're going to do, try to do, is make sure your threads are close to that data. So this is the concept in OpenMP, something to keep in mind. Like I said, the other way around is much more expensive, so that's not done. OpenMP has what we call the Affinity Constructs, and they allow us to control where threads run. So that's what we're going to do. I can't stress that enough. You sort of ought to know where your data is, and I'll get back to that in a minute. But you sort of know where the data is, and then you're going to make sure that the threads that need that data are close to it. Okay, it's very powerful, but you're in charge. It's up to you to get this right, and I want to be clear on that. Right in this context means good performance. You'll always get, if you have correctly parallelized your code, you'll always get the right result, regardless of Numa or not. This is about performance. So when I say it's up to you to get this right, this is about the performance, of course. Right. And you get help through two environment variables. Okay. One is called OMP places. OMP places is a set. You define a set, and that set defines where threads are allowed to execute. And with that comes the nice feature that you can restrict where threads are being executed. You can control, you can exclude things. You can say, I don't want you to run there, I want you to run there. So that's really very powerful, and that's controlled through OMP places, and you'll see several examples of that. You can go down, and that's going to be my example, to the raw, low-level hardware thread ideas, but there's also symbolic names like sockets, cores, and threads. So you can say, I want my threads to run on one socket. I don't care which one, and you shouldn't really care, but I don't want you to go outside of the socket. Or you can say, I want to use the cores in the system, and you can specify how many you want to use. So those are symbolic names, and then the hardware will figure something out. My example is going to be about using hardware thread ideas. That's like the assembly level coding equivalent, but it gives you full control, and I want to show you how you can do that. In addition to that, there's a procbind variable that controls how to map the threads onto those places. And that maybe sound vague, but if you see the choices, it starts to make sense. You can say, I want to be close to the master thread, although I think that's going to be, phased out, that feature. It's not very, very helpful. The commonly used ones are close and spread. You can say, I want the threads to be close because they're sharing a cache and that is really good, and I want them to be close. So, or I want them to be spread out. And those are the choices you have for the procbind. So let's look at an example. Little script. I'm using 16 OpenMP threads. Let's say I just wanted to use 2 sockets. I say OMP places equals sockets, and the number 2 says, give me 2 sockets. Again, you don't know which ones, and you really shouldn't care. But whenever I have threads, I want to spread them as far as possible. So the procbind is set to spread. So you want to push them out. So if you have 2 threads, you would expect that the runtime system will give you assignment to each one of those sockets, not schedule 2 threads into 1 socket. So with spread, you really push them out, and then you run the code. So that's how easy it is to control these things. Now, of course, the devil is in the fact that how do you get to those choices? Right. And that goes back to the question, where is data allocated? How do I know where my data is? And about every operating system I know, I should say multi-user operating system, uses what is called first touch placement policy. What it does, it allocates the page. This is all at the virtual memory data page level. So fairly large chunk of data, 4 kilobyte, 8 kilobyte, maybe larger. But what first touch does, it allocates it in the memory closest to the thread accessing this page for the first time. It really does, as the name suggests, the thread that touches the data for the first time becomes the owner of that data. And that controls where the data will go. The data will be mapped into the memory of wherever that thread is executing, in whatever node that thread is executing. We call that the home node, and that's going to be the home node for that data. And that's fixed. Right. And it makes perfect sense for sequential applications, and that's why it's the default for Linux and other OSs, because that's the right thing to do. It may not be the right thing to do in a parallel application, however. So what if a single thread initializes most or all of the data? That means that thread owns the data. All that data will end up in the memory where that thread executes. That's probably not a desirable situation, because any other thread that needs the data will have to go and get it, wherever it is. It costs time. In the worst case, if there's a lot of threads, you can even get congestion at the memory controller. So all sort of bad things happen then. So this is probably not what you want. Now, luckily, the solution is often, not always, but often surprisingly simple. Parallelize where the data gets initialized, because that's, remember, first touch. That's when you first touch the data. And here's an absolutely trivial example. I have a loop that initializes A to 0. If I wouldn't do anything in terms of parallelization, this loop would be executed by sequentially. And that means the thread, the master thread, the main thread, would own all that data. That's probably not what I want, and you can very easily solve that by executing this in parallel. As you know, the loop will be split up. Each thread will work on a chunk of A, so each thread will have a block of A in its memory. Okay, in that way, I sort of distribute A across the nodes of my system. Okay. A little bit more complex example, but still pretty simple. It's the good old matrix vector algorithm. I'm multiplying a matrix with a vector. In C, I'm using the standard dot product way. And it's extremely simple to parallelize with OpenMP. It's a no-brainer. It's a one-line parallel for, because I'm taking the dot product of the rows of the matrix times the vector. And all those dot products are independent, so I can simply use a parallel for over the outer loop of this algorithm. I hope that's sort of clear. And of course, I need to initialize my data at some point. So that's what I'm doing here. So what's wrong? Well, there's nothing wrong with this code. It's correct parallel code, but it's not Numa aware. In particular, the data initialization I briefly showed is sequential. I didn't use OpenMP there. So wherever I initialize the data, that thread will own all of my data, and it will end up in the memory of wherever that thread is executed. There's a more Numa-friendly way to do this, and it gets more elaborate. In the interest of time, I'll speed up a bit. But what I'm doing here is I'm parallelizing the data initialization. I do reverse engineering on the algorithm. I'm going to see in the algorithm, I know that a thread will get a number of rows of the matrix. So it really should have those rows in its memory. So I'm parallelizing the initialization of the matrix B according to that idea. So the first OMP4 will take a slice of B, a number of rows of B for each thread, and they will all own a part of B. I hope that is sort of clear. I'll skip the one in the red. I also want to initialize the result vector, because that suffers from the same Numa problem. If I don't initialize, this is a redundant initialization. It's a very small effect. It won't matter, but as I say, don't leave anything on the table, but you probably can't even measure it. I just want to show you that sometimes you need to do something that's not entirely obvious. And in this case, that's to pre-initialize the result vector, which shouldn't be necessary from a correctness point of view. I just want to make sure that A is distributed as well. I also distribute C, and in that way, I have scattered my data over the system. All right. Now, before I show the results, I want to show you two useful tools. I use them all the time. There are more than that, but one of them is called LSCPU. It shows you how things work in the system. And there's Numa control that shows you especially about the relative latency. So this is where you can get them if you like to use them. But I want to show the result. So I'm using an older AMD system, and I apologize to people. I do that because this is an interesting Numa box, but since then AMD has made a lot of progress. So don't take me wrong. I just wanted to have a nice Numa box to play with, and this is one. It's the older AMD server. So how can you tell what the Numa topology is? Well, type in LSCPU, and what it will tell you is something like this. And you see the words, you've got a whole bunch of output, but you'll see the words Numa node and followed by a number. So we see the number 0 to 7. So it means there are 8 Numa nodes in this system. We see a column 0 to 7. That means that's 8 entries. It means 8 cores. So each Numa node has 8 cores, and it has 2 hardware threads per core. That's the 2 columns, comma-separated columns. That means there are 2 threads. If there were 3, you would see 3 columns. And these are the low-level hardware thread ideas that I can use to control where things are running. Numa control -H. Oh, I'm sorry, and Numa control -H is really useful. It shows me the relative latency. Scale to 10, and the numbers are not the real latency, there's some relative metric. But what you see when we look at the top line, we see node 0 is connected, of course, to 0, and 7 other nodes, 1 through 7. Its own scaled latency is 10. I don't know, I know why it's not 1, but you would expect it to be scaled to 1, but okay, it's 10, that's the normalized. Then we see 3 nodes that are further away. They have a latency of 16, so they're further away. Again, you can't take this as the real latency number, it's some sort of it, but definitely these nodes, 3 nodes are further away. And then there are 4 nodes, 4, 5, 6, and 7 that are even further away. So I have 2 levels of Numa in this box. So from this output, what I learned is there are 8 Numa nodes. Each Numa node has 8 cores. Each core has 2 hardware threads. So in total, I have 64 cores and 128 hardware threads. And there are 2 clusters with remote nodes. One cluster has some sort of latency of 16, those are 3. And there are 4 others that have a higher latency, and I label them 32. All right. So that's what we learned from this output. It's very, very valuable. It allows you to make a diagram like this. So I have my center node. My center node is connected to 3 remote nodes with a longer access time, the 16 class of nodes, and 4 that are 32, labeled 32. So I have 2 levels of Numa in this system. Right. So zooming in a bit on those numbers, here I show you the numbers, the thread numbers for node number 0. We see we have 8 cores, that's the yellow box, and in those vertical bars are the 2 hardware threads. So the 2 hardware threads in the first core are 0 and 64, not 0 and 1. In the second core, the first hardware thread is 1, the second one is 65, and so forth. That's what we get from those numbers. So now we know exactly what the system looks like, and we can address those individual hardware threads at the OpenMP level. So that's what we do with the OMP place. Okay, I just said this a little while ago, and I said they're preferred to be used, but sometimes you want to go for the low-level numbers, and that's what I'm going to do. Okay. So let's say I set myself the goal to distribute the OpenMP threads evenly across the cores and the nodes. I want to spread them out over my entire system. For example, I want to use the first hardware thread of the first 2 cores of all the nodes. Okay, I'll show you a diagram what I mean with that. Okay. So this is what I want to do. Node 0, I want to use the light blue bar. That's the first hardware thread in the core. And that number we know is 0, 1, and so forth. That's the first hardware thread in each core. And likewise, in the second node, it's 8, 9, and then we've got 16, 17, 24, 25. So when you look at those numbers for a while, you'll see that these are the numbers that will give me the access to those hardware threads in these cores. So how do I do that with OpenMP? Well, recall this was the LSCPU output. And I'm going to define my places using the set notation supported in OpenMP. The first one, I start with 0. That's in the curly braces. I want to have 8 elements, and the stride should be 8. The next part of the set starts at 1. Again, 8 elements with a stride of 8. And altogether, that gives me this sequence of numbers. And when you go back and look into the diagram and the LSCPU output, you see that that's exactly what I wanted to accomplish. In this case, it doesn't really matter what I do, but I want to keep them close. And I'm using 16 threads. I have 16 places, and I want to use 16 threads for them. Note that when you go this way, I use OMP display env, the environment variable. It's really helpful because it echoes your settings. It has saved me more than once. And here's the result. I'm showing this for 64 threads. In a CPU intensive algorithm like this, using hyperthreading doesn't make much sense. So I'm not using my 128 threads. I'm using only the first thread for each core. I see the performance. Don't look at the number precisely. This is not the fastest algorithm. It's my homegrown algorithm. But what I want to show you is that without the Numa tuning, without modifying the data initialization, I get that purple dotted line, and I barely get any scalability. When I start doing the Numa stuff, I see some funny behavior in between. I didn't really look at that, but it's kind of interesting behavior in between. But altogether, I get a performance improvement of factor of 22. Oh, I'm sorry, a factor of 22. So just by modifying my data initialization, I didn't modify my algorithm. I only modified my data initialization. So keep that in mind. That's how important this can be. All right, the takeaways. I hope to have shown that data and thread placement matters, and it could be a lot. Leverage first touch. It's a great way to figure out where your data is. I do think OpenMP has very good, powerful support. It's very hard to make this abstract and powerful and generic, but I think the committee working on this did a great job. More has been added in 5.0 and 5.1. And brings me to the final tuning strategy. Again, always use a profiling tool. Don't forget serial performance. I didn't talk about data structures. That could be another talk maybe. You may want to spend time, oh, excuse me. You may want to spend time on looking at your data structures. Again, that wasn't even touched upon in this talk. Look at those cases like barriers, redundant barriers, too many parallel regions, and those kind of things, what I call the low-hanging fruit. Address those. And again, don't forget about data placement. And what I call is think ahead. Even when you see some small inefficiency, fix it, because what may not matter today may matter tomorrow. All right. Thank you. Stay tuned. And remember, it's not that OpenMP doesn't scale, it's that bad OpenMP does not scale. So, sorry for running a little over. I hope you found this useful, and we can start looking, as far as I'm concerned, we can start looking at the Q&A.
Okay. Great, Ruud. Well, we could, go ahead, Lucy.
No, you go ahead, Kathleen.
Okay, there were some questions that were already answered, but I don't really have a way of knowing if they were answered sufficiently or to the original requester's satisfaction.
Okay.
So
I have them in
for
front
now,
of me.
Great, then let's just have you take it from there.
Okay, yeah. Let me see. All right. First question, is there an easy way to deal with dynamic scheduling and Numa? No, not really. No, that's because you don't know where threads will run. I guess that's what's behind the question. Unfortunately, no. One thing that I found useful, for example, in graph analysis, when you have random memory access and it's really hard to get data localization, is sort of distribute the data equally across the system and live with some sort of higher overall latency, but at least uniform. So you kind of make it a bit worse, but it's uniform. So that would be my initial recommendation. Let's see. Okay. How to parallelize loop with loop candy? Well, unless it's a very special case, the loop carry dependence.
Ruud, would you please repeat the question before you answer it?
Oh, I thought I said that, but okay, this is fine. Wait a minute, where's? Oh, sorry, I skipped the question. Let me do the second question from Mats. Why not have PragmaMP master? Yeah, I'm not sure it's cheaper than single. I don't like the fact that it doesn't have the barrier. I'd like to be explicit about it. So also anybody else reading the code, maybe not so familiar with the intricate details of OpenMP, will see that I add a barrier. But yeah, you could do master. Not sure whether there's a lot of difference, but sure, yeah, yes. But as the comment is, I think it's deprecated as indeed. I think it will be phased out. I don't know when, but I think the plan is to move away from it because single and a no wait will accomplish the same. So, but yeah, at this point it will be equal. So yeah, the loop with the loop carry dependence, you can't just straightforward parallelize those because the algorithm is inherently not parallel. There are ways to sometimes transform a loop carry dependence into something parallel. Usually you take a hit in terms of the efficiency, so it may be slower in sequential mode, and then you can parallelize. But once you go that way, you got to be careful that the slowdown is not impacting you too much. So in general, you can't do that. There's one thing for like wave type of solvers that OpenMP has. The name escapes me now for the moment, but there is a way to do certain type of wave-like finite difference kind of schemes. All right. Let me see. Is there minimum duration? No. Is there a minimum duration? In other words, when is it efficient? I think that's the question. That does depend on your system. What I find that if you write the efficient code of open, if you write it efficiently, it's very sort of generic gain that you have. You could do, of course, theoretical sort of observations like what's the cost of this and what's the benefit. In general, when you do, you won't, if you have an initialization loop that is 4 elements long, you wouldn't run that in parallel. Yeah, so there is some sort of gray area where things do not make much sense. Again, that's why you want to use a profiling tool to actually guide you. But so there are no rules of thumb, I think. Okay. Page 12. Oh, I'm not sure what page. Okay, I see that Mats already applied. Yeah, that was a very controversial thing that you didn't know who would pick up the next portion of work. That has been formalized now, and the OpenMP is doing what most people expected it to do. So pick up the same work, so you also get some cash benefits. And so today the runtime system tries to do the smart thing and especially exploit the fact that things may still be in the cache of the thread executing it. So the next block of code will be sort of split up in the same way. I didn't really, at that point, I didn't turn off hyperthreading, but yeah, that's something, you don't have to really disable hyperthreading. I know sometimes it works in terms of performance, sometimes it doesn't. As I was showing in the last example, that's why I did that. By controlling the mapping of OpenMP threads onto the hardware threads, you effectively not use that hyperthread or those hyperthreads. You may want to, disabling them entirely is rather brute force. You may not have that control on your system, but at the OpenMP level, you can just say, I choose to ignore them. The thing is that I find that very hard to do with the prefabricated keywords like threads. And I know I'm more like an assembly hacker maybe at that level, but I usually go for the numbers. But that's hard to get when you get started. When you get started, you start saying places equals cores, and you see some benefit, and often that gets you going. These are good ways to use it. But when you really want to have that fine control, use those numbers, and in that way, use whatever hyperthread or not use whatever hyperthread there is. Let me see. Would it be a good idea to if clause? Yes, yeah, definitely. I want to dig deeper into that. So tasking could be a very good alternative to dynamic scheduling. Not always, though. We shouldn't forget that these things from the past do have value. So it's not guaranteed, but it's certainly worth considering. Yeah, you're in for some experimentation. Okay. Yeah, exactly. That's I think the first question. Sorry, I'm doing this in the wrong order. Yeah, so you want to as a fine tuning, you can pre-initialize the result data structure, and in that way spread it out. And that's indeed what I was doing. Let me go to the new questions. Okay, I think we got, for now, we got all the Q&A from here. I'm not sure whether we have a formal way for people to send questions other than the forum, of course, but we definitely encourage you.
Yeah, we do.
Yeah.
We do have the OpenMP forum that you can access on the OpenMP website,
Right.
and so you can always submit questions there. Of course, that won't go directly to Ruud. That'll go to everybody in the OpenMP area.
Yeah, I'm not
and
often on
actually,
that forum.
any OpenMP user.
Yeah, but many of us
But-
are on that forum, and they're more active than I am. Unfortunately, I usually lack the time to do that, but that's not an excuse. So yeah, we do try to keep track of what's happening on the forum and answer your questions there. Yeah.
Yeah.
Maybe also post
All
ideas
right.
for this seminar. Yeah. Okay.
All right.
Well,
Lisa, you want to wrap it up?
Sure. Thank you everyone for joining. Like I said earlier, we will have, you'll be expecting an email tomorrow that'll give you a link to bring you to the recorded presentation and more information about OpenMP. So check back and stay tuned. We have more webinars coming from OpenMP in the future. So stay tuned. Thank you very much for joining.
all right. Thank you. Thank you all for listening and staying on. That's nice. Thanks.
Bye, everyone.
Bye.
Bye-bye.